Hello, my name is Debottom Ghosh. I am in CSE 5th SEM at Ramkrishna Mahato Government Engineering College. Today, I will discuss asymptotic analysis and complexity bounds, base case, average case, and worst case from my PPT. Then, what is asymptotic analysis? Asymptotic analysis of an algorithm refers to define the mathematical framing of its runtime process. Means it is a standardized way to describe the efficiency or complexity of an algorithm and function. It allows us to analyze how the performance of an algorithm or the growth rate of a function behaves as the input size becomes arbitrarily large. Using asymptotic analysis, we can very well conclude the best case, average case, and worst case scenario of an algorithm. Then we will discuss the types of asymptotic notation. There are primarily five types of asymptotic notation: big O notation, big omega notation, theta notation, little o notation, little omega notation. Then we will go to the big O notation. What is big O notation? Big O notation, this is perhaps the most commonly used asymptotic notation. This big O notation is a formal way to express the upper bound of an algorithm's running time. It measures the worst case time complexity or the longest amount of time an algorithm can possibly take to complete. For example, if we take a function fn, big of fn equals to gn. There exists a value constant c which is always greater than 0 and a value n0 such that gn less than equal to c into fn for all values of n greater than n naught. In this image, we will see that c of gn always greater than f of n. At the point of n naught, c of gn equals to fn. If we take an example, let us consider a function fn equals to 4n cube plus 10n square plus 5n plus 1. We always know that the greatest coefficient of n, we take that gn. So gn equals to n cube, and if we the constant c value, if we take 5, then fn always greater than equal to 5 into gn for all the values of n greater than 2. Hence the complexity of fn can be represented as big O of gn, that is big O of n cube. Then we go to the next point or next type of asymptotic notation, big omega notation. What is big omega notation? It provides a lower bound on the growth rate of an algorithm's complexity. This notation is a formal way to express lower bound. It measures the best case time complexity or the best amount of time of an algorithm can possibly take to complete. For example, big omega of fn always greater than gn. There exists a constant value. This is also a greater than 0 and the value n naught such that gn less than c into fn for all values of n greater than n naught. If we take an example, at first we go to the image. We see that fn curve is always greater than c into gn. Here also at the point of n naught, fn equals to c into gn. Now we go to the example. Let us consider a given function fn is equal to 4n cube plus 10n square plus 5n plus 1. considering Gn equals to Nq, we know that the greatest coefficient of n, that we take Gn. So the constant value C, if we take that C is equal to 4, then if n greater than equal to 4 into Gn for all values of n greater than equal to 0. Hence the complexity of Fn can be represented as big O of Gn, that is big O of Nq. Then we go to the theta notation. What is theta notation? At first, the big O notation and big omega notation, we see that the big O notation consider the upper bound and big omega, that is the lower bound. But the theta notation combines both the upper bound and lower bound to provide a tight bound on the growth rate of a function. This also, while the big theta notation could almost accurately used to describe the average case, other notation could also used as well. It represented as follow: theta of Fn equal to Gn if and only if Gn equal to big O of Fn and Gn equal to big omega of Fn for all n greater than n naught. Let go to the image. We see that Fn is the middle curve and upper curve and the lower curve, means the upper bound and the lower bound here we see. Let us go to the example. Let us consider a given function Fn is equal to 4nq plus 10n square plus 5n plus 1. Here also we know that the greatest coefficient of n equal to is the value of Gn. So we take Gn equal to nq. Here two values of constants C1 and C2 are used. C1 is used for the upper bound and C2 is used for lower bound. For the first constant, that is the for upper bound C1, we take the value as 5 and the lower bound value C2 we take 4. So we see that 4 into Gn less than equal to Fn less than equal to 5 into Gn for all values of n. Hence the complexity of n Fn can be represented as theta of Gn, that is theta of Nq. Let we go to the two notations, little o and little omega. The little o and little omega notation also represented the best and the worst case complexities, but they are not asymptotically tied in contrast to big O and big omega notation. Therefore, most commonly used notation to represent time complexities are big O and big omega notations only. Let we go to the image, means graph. Here we see 5 graphs, that is 5 graphs means 5 lines. Big O, little o, if in that we take the function little omega and big omega. So here we conclude that asymptotic notation help in performing analysis of the runtime behavior of an algorithm. Using this, we represent the upper bound or lower bound of runtime in mathematical equation and thus helps us perform our task with the best efficient and fewer efforts. Asymptotic notation is essential for comparing and analysis algorithms without getting lost in the details of specific implementation or constant factors. It helps us understand how algorithms performs as inputs grow large and aids in making informed decisions when selecting algorithms for specific tasks. By focusing on broad growth trend on functions, asymptotic notation simplifies the analysis and design of efficient algorithms. And now, thank you. This is my the PPT, and this is all for asymptotic analysis and complexity bound. Thank you.